Hi everyone, my name is Saeed and today I will be talking about covering points with pairs of concentric disks. This is a joint work with Anil Maheshwari, Sasanka and Michiel Smid. First problem statement, a pair of concentric disks is two disks with the same center where one has radius 1 and the other one has radius 2. And as the input to our problem, we are given m pairs of concentric disks and n points in the plane. So here, for instance, I have 5 such pairs and a set of points. And the problem is to select exactly one disk from each pair such that all points are covered and the number of points that are covered by at least one small disk is maximized. Okay, so for example, if we select it this way, so I'm selecting exactly one disk from each pair, then we count the number of points that are covered by at least one small disk. Here I have 4 of them, so the objective value is 4. Okay? Note that even if a point is covered by more than one small disk, we will count it as still just 1. Okay, so we actually looked at both 1 and 2-dimensional space, where in 1D, we show that the problem is polynomial time solvable. We looked at 2 different variants, where the first one, we have a kind of a special case. And then we looked at the general case, where our algorithm runs in order m squared n time. And then for the case of 2-dimensional space, we showed that the problem is NP-hard. Okay. Here I will first show the special variant in 1-dimensional space, where we call it a left align, meaning that if in the table here you look at the top case, the black and blue interval both have the same left x coordinate. So their left endpoint has same x coordinate, and that's what we call as left aligned. So we assume that all input intervals are left aligned. And we give a dynamic programming that runs in order m n times. Some notation for our table. A of ij denotes the objective value of an optimal solution for the first I points and the first j pairs, where we sort the points and intervals from left to right. And bij is the objective value of an optimal solution for the first I points and the first j pairs, assuming that the larger interval of the jth pair is in the solution. Okay. Now we show how to decompose these two. First, A of ij. In order to decompose A of ij, we look at 2 cases. First, consider a vertical line L that is passing through the right endpoint of the smaller interval. Okay, so we call that L. And also consider L prime, the vertical line that passes through the left endpoint of the intervals. Now we consider 2 cases depending on whether Pi, which is the last point in this subproblem, to the left of L or to the right of L. Here I'm assuming first, let's say it's to the left of L. Okay. And this is the last pair, or O sub j, the last object that we are looking at. Then we can decompose the problem into A of I prime j minus 1, where I prime is the point I prime that is the rightmost point to the left of L prime. Okay, plus the number of points that are covered by the smaller interval of the last object or the last interval. because if in this case we selected a small interval, then we get a score for all of these points, and then the problem is reduced to a of I prime j minus 1. In the second case, we assume P sub I is to the right of L. And in this case, we will need to look at both last pair and the pair before that. So OJ, OJ minus 1. And then we look at 3 lines. L is the same, the line through the right endpoint of the smaller interval of OJ. Then we look at L prime, which is the line through the right endpoint of the smaller interval of OJ minus 1, and then L double prime, which is the one to the left through the left endpoint of the OJ. So L, L prime, L double prime, we define the points similarly. So PI is to the right of L, PI prime is the rightmost point to the left of L, and PI double prime is the rightmost point to the left of L double prime. Okay. And if we define this as I mentioned, then the problem we can decompose for Aij as the maximum of Bi prime j and Bi double prime j minus 1 plus the set of points covered by the smaller interval of Oj. Now, the reason for that is we have the results saying that if Pi is to the right of L, then we can only focus on selecting whether Oj or Oj minus 1. We can only focus on the last two, and we don't need to look at the other. And depending on which of these two is selected by optimal, excuse me, we can get these two sub-problems from which we will take them the larger or the maximum. All right, so that's how we can decompose A of Ij. And as you can see, we can fill out each entry of Ij, A of I, in constant time. And therefore, filling out the entire table will take us order mn time. Then Bij is actually even simpler. We can decompose it in a very similar way. So I will skip that part. But as I said, filling each entry will take for both tables constant time, and therefore it takes us order mn overall time. Now for a one-dimensional general case where we don't have this restriction of being left a line, the smaller interval can be anywhere within the larger interval of every pair. The idea is the same. We apply, again, a dynamic programming where we look at the last pair and we try to guess which one is going to be in the optimal solution. However, here we, in some cases, cannot rely on only one pair, and we need to guess a pair of intervals in an optimal solution in order to be able to decompose the subproblems. And when we get a pair, therefore, we get order m square n running time. So that's why we got m square. Now let me move on to the two-dimensional case where we show a reduction from the variable restricted planar 3-sat problem. So let me briefly explain which variant is this one. So on the left, I have an instance of variable restricted planar 3-sat. So it's a version of a 3-sat problem where we can draw the variable clause graph in a planar way, such that the vertices of variables are all lying on a vertical line, and then the clauses are connected to the variables from left and right, such that each variable appears in at most 3 clauses. That's why it's called variable restricted. So we know that the degree of each of the vertices corresponding to variable is at most 3. Okay. So given such an instance, and crosses here are indicating the negation of that variable. So if I have a cross on one of the edges, it says it's, let's say here, x bar, x2 bar. Now we take such an instance and we want to construct an instance of our problem. First, we replace each variable vertex with a variable gadget that looks like the one on the right. Okay, so it's 2 pairs of concentric disks, and in the center or within the smaller disks, we insert a set of points. So this is kind of showing a set of points whose value will be determined later. And we also insert a set of points here in the intersection of the larger disks. Okay, and so as you can see, I will need to cover these points in any solution, and therefore at least one of the larger disks has to be selected, which will then force its a smaller disk not to be selected. Okay? And that will correspond to our xi and its negation, xi bar. So that's how we create two different ways of covering this set of points, and therefore corresponding to whether we set the variable to true or false. Okay, so that's the variable gadget. Then from variable gadget, let's say xi, we had at most 3 edges incident. This is how we try to connect these variable gadgets to the class gadgets that I will show in a second using wires. And so here I'm showing, for example, one of the variable gadgets, the 2 blue pairs. From there, we are taking out this set of wires, which is very similar to variable, but now we repeat the same thing. And the number of points that we insert in each of these will be different and determined later. We may sometime have some turnaround if, let's say, I have all of them going to the left, but I am taking, let's say, different copies of a variable, then I may need to do a turnaround, but it's still polynomial in the number of pairs that we will use to build the wires. Okay. I will not go through the details here, but depending on whether we set the variable to true or false, there will be 2 different ways corresponding to those of covering all these points, depending on which of these we select. It will be either, let's say, the big disk of this pair, the small one, the big, the small, or it alternates the other way. And depending on how we cover, on the other end, they will meet at a class. So this rectangle or box is showing our class gadget, where this chain of disks are meeting all of them in the center, where we again insert another special set of points. And we argue that in order to cover that set of points, at least one of these wires or this set of chains has to be selected in a way that the corresponding variable is set to true. Okay, so that's again kind of a high level description of the reduction, but putting everything together, we can show that by this reduction, our problem in 2D is NP-hard. Okay, let me just conclude. The problem is polynomial time solvable in 1D, but it's NP-hard in 2D. For future work, improving the running times of our algorithms for 1D is one direction. And the other direction is we were not able to find an approximation algorithm for our problem in 2D? Can we obtain a constant factor approximation? Or does the problem even admit a p-TOS, or it's APX hard? Okay, so I think those are the more interesting questions or problems to work on or answer. Approximability status of the problem in two-dimensional space. With that, I thank you very much for your attention, and I will be happy to take if you have any questions. Thank you very much.